Hello to all the HubLE audience. My name is Jonathan Gustafson. I'm a postdoc research fellow at Rush University Medical Center in Chicago, and I am also co-chair of the Meet the First Author Committee at HubLE. I'm here today for an edition of Meet the First Author with Dr. Jessica Hathaway-Schrader from the Medical University of South Carolina in the United States. And we will be talking today with her about her paper titled Specific Commensal Bacterium Critically Regulates Gut Microbiota Osteoimmunomodulatory Actions During Normal Postpubertal Skeletal Growth and Maturation. And this was published in JBMR+. So Jessica, welcome to HubLE.
Thank you. Thank you for having me.
We're really excited to have you talking about your paper today. And so what I'd like to start off with is that there was a big picture emphasis in this paper about the gut microbiota and how that contributes to bone. Can you tell us a little bit about your background and work in this field and how the microbiota kind of contributes to bone and bone regulation?
Okay, so our lab studies osteoimmunology, which is the regulation of the immune cells on the bone cells. And we've previously published in this area looking at just normal mice compared to germ-free mice, where we saw that there was an increase in bone volume in germ-free mice, which don't have any microbes. And because of that, the work that we found in our previous paper in scientific reports, we built on that story, looking how we found between the gut liver bone axis and how that can really regulate the skeleton. And so because of that previous work, we found that we wanted to dive into really specific microbes and how they can also have this effect, whether it could be one microbe or a collection of them. And so that kind of led us into the paper that we published recently in JBMR+, is that we found that there's been previous work looking into this one microbe called segmented filamentous bacteria, or SFB. And so a lot of the work on that one microbe has been done in the immunology field, where they look at it in the gut. However, our question was, because it's part of the commensal microbiota, does it also have an effect on the skeleton? And so with our paper that we published, we actually found some interesting results that this one microbe can have effects outside the gut, through the liver, and having an effect on the skeleton, specifically with looking at in the postpubertal phase. So yeah, go ahead.
Okay, no, that's great. That's excellent. So that's a really great overview, kind of talking about the field, because the microbiota has been really such a hot topic in the research field, right?
Yes, very much so.
So the clinical application that everybody, I think, is trying to go towards is being able to have some targeted applications of being able to take maybe some type of supplements or some way to be able to affect your gut microbiota and these specific communication and signaling pathways to be able to try and control either bone resorption or changes like that, right?
There's actually a couple studies that have already come out in terms of the aging skeleton, where probiotics have had a beneficial effect with the skeleton. However, with our work, we're actually looking at a much earlier time point, where we look at the postpubertal phase, which, during that phase, we can collect or really accrue up to 40% of our peak bone mass. So what we're trying to really capitalize on is really attaining that really peak bone mass, so that as you age, you really are kind of weathering that storm of the age-related bone loss. And so with that, that's where we would really want to look at more of a preventative application of probiotics or what have you to target specific microbes during that phase.
Excellent. So now with this specific paper, you talked about the SFB microbe in particular that you were interested in exploring. So why specifically this microbe? Is it just kind of based off the preliminary work? And can you tell us a little bit about, in your paper, what you've specifically focused on and what you were measuring within the bone that you feel kind of indicated? And it wasn't just bone that your paper also looked at.
So really, SFB has been very well characterized to drive Th17 IL-17 immunity. So that's a specific immune cell that really drives that pro-inflammatory IL-17 response. And there's tons of literature on looking at SFB in the gut and how the interactions of SFB with specific cells in the gut drives this immune cell. Well, that immune cell also is really very important in terms of pro-osteoclastic actions in the skeleton. So we were able to really kind of connect the way of how SFB can have these effects outside the gut to lead towards this more pro-osteoclastic phenotype. And so with our previous work, where we really kind of lead to thinking that in part that it's a gut liver bone axis, not just a gut bone axis. We then looked in the liver, and there really is very little in terms of looking at SFB's actions on the liver. So we were looking at gut, liver, and the bone, and how SFB can have all these different effects throughout basically the systemic effect.
Interesting. So now with your specific study, you obviously had some mouse model to be able to do this. Can you talk a little bit about that? And then in particular, some of the techniques that you had to undergo, because now you're not just looking, say, at micro CT and trying to look at some of the different cells within the bone, but now you're also looking at the liver.
Oh yeah, we did. There's a lot of different things we had to do, really, to kind of show all these different actions of SFB. So the different mouse models we used, we looked at a germ-free mouse, which is devoid of all microbes, so no bacteria, no fungi, no viruses. It doesn't have anything. And then we compared that to an SFB monoassociated mouse. So we were able to establish a mouse where it only had SFB and no other microbes. And that's kind of how we started out the paper. We just wanted to look and see, how does this one microbe have an effect on the skeleton alone? Okay. And then, luckily, we were able to actually, with the help of one of our co-authors, Dr. Westwater, she told us that Taconic actually has really changed out how they have different mouse models with their specific barrier facilities. And so they were able to establish colonies where one has an excluded flora, so it has a normal microbiota but no SFB. Okay. And then they actually have a murine pathogen-free, or MTFA, where they have a complex microbiota with SFB. So we were very, very lucky that we were actually able to also compare SFB in a complex microbiota with compared to a mouse that doesn't have it, but still has a normal commensal microbiota. So we were actually very lucky to really figure out that we could use SFB alone and then also within the commensals. So.
That's excellent. Very exciting. So now in terms of when we talk about microbiota, obviously one thing that always comes to people's mind is diets, right? So is that something that you controlled with these mouse models in terms of what they were fed, or how did you kind of control that aspect?
They were all fed the same diet, so nothing was changed in terms of like how they ate or anything like that. The only way that really would have an effect in terms of diet is if we were supplementing them with something, which eventually that will be future directions beyond the scope of this paper, but eventually that will be something to look forward into.
So now when we talk about, especially in this case for this paper, trying to connect and bridge between the gut, the liver, the bone, it obviously can present challenges. So what would you say was maybe the single greatest challenge, and how did you overcome that with this paper? So obviously you talked about the collaboration being great because you could now look at this other mouse model, the MTFA. But what else could you kind of elaborate on that was really important for this study that you were able to kind of overcome?
I think the biggest challenge was just, the fact that we look at bone and then my background with immunology, so I know how, at least, flow cytometry, things like that. But I think our biggest challenges was making sure that these mice express the microbiota the way that we thought they did. So testing for SFB or testing for the different phylum of bacteria, because it was outside of our normal expertise. So we collaborated with a couple people, and as well as reading a lot on how to test basically the composition. I think that was the biggest challenge, but at the same time, it's also the most critical, so that we're saying that, yes, this one mouse has only SFB, and then these other two, they have complex microbiota with or without SFB. So, it's absolutely 100% the most important piece of the whole paper. So.
Great. Well, that's obviously an innovative part, is being able to expand your collaboration and know that, okay, we may not be experts, particularly in this aspect. So that's really great that your group was able to identify that and kind of come up with a really great finding. So if you could take away the single greatest finding from this study and where that's going to take you for future directions, could you tell the audience a little bit about that?
I think our biggest aspect is that we found that with SFB in the complex microbiota, that it has the most pro-osteoclastic, anti-osteoblastic actions during the post-pubertal phase, and that it's driving a antimicrobial ligand called lipocalin-2. So lipocalin-2 has really been kind of highlighted in the last couple meetings we've been to, where it's really important for bone metabolism. And what we found is that because of SFB, we see an increase in lipocalin-2 in the liver and as well as in circulation to then have an effect on the bone. And that's actually going to be the most critical piece from the paper, because we're going to be further pursuing that in other different models looking at lipocalin-2.
Excellent. Very great. Now, to tell the audience, so you are a postdoc researcher currently in South Carolina. So for anybody out there watching that's looking for a great junior investigator, obviously, and interested in anything related to microbiota, bone, and especially now liver, obviously be on the lookout for Jess. But in terms of your future career and your career goals, how has this publication helped you, or how do you feel it will help you?
This has actually been very enlightening, really expanding my background in terms of bone biology as well as in osteoimmunology. Hopefully pursuing this as in academia, since I just submitted a K award recently. So hopefully that gets scored well, and hopefully I can continue pursuing this here in this field.
We will keep our fingers crossed for sure. Congrats. That is a huge accomplishment, being able to even submit that. So that's great.
Thanks.
Well, we definitely appreciate you taking the time to discuss your paper today. We definitely would love to hear more from your group in the future, and we would definitely love to take the time to thank the audience today for joining us for our Meet the First Author initiative. You can feel free to reach out to us through HubLE.org, and please keep an eye out for us at future meetings. You can follow us on LinkedIn, Twitter, YouTube, and Instagram. And again, Jess, thank you again, and congrats on the great paper.
All right, thank you so much.
All right.